So today we're going to study memory, and the first question to ask yourself is, why are we taking memory in a class on the senses? And that's because what you sense is surprisingly more from what is stored in your memories than what you actually perceive at the moment. Okay, when you hear me talking, what you hear is not only what your auditory system is decoding at the moment, but all that decoding is based on years and years of learning to recognize what you're hearing. When you're during the first 6 months, remember, you were learning how to recognize the ba's and the ga's and whatnot. And then later on, you learn to recognize words. And all this learning is stored in your memory. So when you hear things, the whole memory process kicks in, and it's trying to compare what it's hearing to what you learned before in order to decode the words. All these programs now that try to go from speech to text, or Siri hearing you on your iPhone, Siri only works well when it's connected to the web, and that's because it stores on the web your speech patterns, and it learns from those speech patterns what you're saying. And so when you say something, it quickly goes down the web and compares it to what you said before, and then sends back an interpretation of that.
Have a listen to this. Sounded strange, right? Have a listen again and see if you can get anything. Still strange. Now listen to this.
I think Brexit is a really terrible idea.
Which I do. So you heard some words there, right? Now listen to the first sound again. I'm just going to replay it. Yeah?
Now you can understand what it said.
Once more for love.
Just because somebody explained what it was being said. So
okay, so what's going on here is the remarkable thing is the sensory information coming into the brain hasn't changed at all. All that's changed is your brain's best guess of the causes of that sensory information, and that changes what you consciously hear. Now, all this puts the brain basis of perception in a bit of a different light. Instead of perception depending largely on signals coming into the brain from the outside world, it depends as much, if not more, on perceptual predictions flowing in the opposite direction. We don't just passively perceive the world, we actively generate it. The world we experience comes as much, if not more, from the inside out as from the outside in.
Okay. So, that's why we're studying memory. Now we'll go figure out what memory is. Now, when you say the word memory, it can mean two things. It can mean your memory of grandmother, what grandmother looks like, what she sounds like, what kind of things she did. All these are memories, or what you think of as memory. But also memory is what stores your memory of grandmother. What mechanism is it? Where is that mechanism? And exactly how that memory is permanently inscribed in your brain. Now, learning is the storage process. So it's how you sense something and learn from that sensation. And that's mediated by synapses that change their strength. That's a simple and only thing that is involved. How it all works, we still don't know. And what we don't know is remembering. So how do we remember things? You see someone, you remember that person's name. How do you retrieve that name from your memory? We're still not quite sure how that works. So in terms of memory, there are various types of memory. We took one already called short-term or working memory. You can see here examples of it being used. It's words being said, or as you see here, numbers being added. All these things are part of your working memory. And that involves this area here in your frontal lobe. And has a very limited capacity, so it can't store much at any one time. You can only tend to remember something like a 9-digit number, if at best. Now, from short-term memory, things are loaded into long-term memory. And one of these is called procedural. So procedural is knowing how to do something. And it includes skills like skiing. And it's established slowly through practice. It takes you many tries to learn how to ski. But you're not conscious of that ability. For example, when you stand up, you're not conscious of the ability of standing. It's all ingrained in the neurons that control your legs and your vestibular system and whatnot. And it's not affected by amnesia. It begins at birth, and it's stored in various places around the cortex. We talked about how V1 cells are trained to become binocular. They're during a critical period. Motor cortex is involved in changing synapses. The cerebellum is involved in this learning process. It's where the skills of all your movements are stored. So those are long-term but procedural memories. Another type is declarative. So knowing that. And it represents sort of your memory of objects. This is a mouse, this is a laptop, and events. So when your birthday is, stuff like that. And also it involves associations. So every object has associations. So the mouse might be associated with a laptop, and a friend's birthday is involved with the memory of having a birthday party the previous year. And one is conscious of remembering. You know that you know this person, and you know that you know this person's name. It doesn't begin immediately after birth. It takes a while to develop. And it is affected by amnesia. And we'll discover today that learning involves a structure called the hippocampus, located in the underside of the temporal lobe, on the medial, in the middle of it, so medial temporal lobe. And so the hippocampus is involved in learning, but it's not involved in storing that memory. So it forms these long-term memories, but the memories themselves are located in many parts, many association areas, but in particular, other inferior temporal lobes. Like, remember, the fusiform face area is part of this inferior temporal lobe. That's where you remember where the visual aspects of faces lie. Okay, and then we'll look at it. So in declarative, there are two types: semantic, and in a moment we'll look at episodic. Semantic is, remembering the faces and the places. And we mentioned that there's a fusiform face area located here. So you can see that it lights up if a face were shown, but now a place is being shown. So this lights up an area just beside it, called the hippocampal place area, PPA. And so various places, like where's some image from Eiffel Tower in France. And then we have episodic. They're like semantic, but they're more complicated because it's many objects and places in your personal past. So it associates who and what with where and when. So it's composed of several semantic members. So many of these compose one of these. So here is a picture of my 3 kids when we were in Paris while I was on sabbatical. We had a wonderful sabbatical year. And these kids now are grown up, and they each have 2 kids of their own. So when I see this picture, it brings back all those memories. It also involves storing like a sequence of places that one passes as one drives home. So you develop a map of the city that you live in. Okay. Now, the areas that are activated by recalling these memories are the same areas that are activated during perception. So we know where these memories, so when you remember things, they activate the same areas that are activated when you perceive them first. So when you remember a face, that lights up the fusiform face area. And if you don't have the fusiform face area, then you can't remember that person or recognize that person when you see that person. But of course, you can remember that person from other cues, like auditory cues. You can remember the voice. You can remember the gait. So all these memories are stored elsewhere. So the complete person is stored in many places. Okay, working memory. We'll look at that for a moment. What I'll show you in a moment is a bunch of words that will appear one at a time, and your task is to remember them. And we'll learn some properties of how the visual system or how working memory works. Okay, ready, set, go. Okay, so we'll wait a little bit, let you hold it in working memory. Did you see this word? Yes. Good. And so that was easy because it was the last word on your list. And so it's easier to remember what was loaded last in the working memory. Well, still a few nods, but that's harder to remember. So it's good that you remembered it, because working memory has, as I said, a limited capacity. And as you put in things into your working memory, things get shoved out. And it's usually the oldest things are shoved out. What about this one? Oh, still a few nods. Okay. This is harder because it's not a real word. So it's harder for you to develop associations with it. It's harder for you to store this word. Okay, so we've looked at working memory one type. This is for words. But there's also a working memory for locations. You can remember where things are in this room. Just close your eyes and you can remember possibly where some people are in this room. And you can remember objects that you have in this room or other objects. The interesting thing is that if we fill up this one with words, these two are still empty, and you can still add things to these words when this one is still full. So each one has its own sort of place where it stores, and each of these has its own limited capacity. Okay, another aspect of working memory. There'll be some strange objects that appear. You're supposed to look here, and there's two objects that appear, one over here and one over here. And you're, without moving your eyes to either of them, the idea is, can you tell whether they're the same or different? Okay, were they the same or different? Everyone for the same. Not many hands. Everyone for different. Everyone. Perfect. Yes, it's different. Okay, this one. Same? Everyone's for same this time. Good. Oh, maybe that's it. That's it for the test. So, what did we learn here? Well, we were looking at the center, and these objects appeared at two sides. So they're in different parts of your retina. How was it that you compared these objects? Well, these objects are transformed. They're objects, so they're stored in their own object's allocentric frame. So in your frontal lobe, you can store them with their center in the center, and then you compare the two, whether this one was the same as the other one. So it's not stored where it was in the retina, but it's stored in an object representation, object center coordinates. Now, how is working memory formed? Well, working memory is something temporary. So it involves something like these reverberating circuits, like the reverberating circuit that we saw for storing eye position in eye movements. Remember that one? The PPH. Well, you've got lots of these circuits in the frontal lobe. And the transmitter here is dopamine. And so dopamine is an important thing in the frontal lobe to be able to store all these memories. And very recently, they did an examination comparing how much dopamine there is in the human cortex compared to that of other primates. And in the human cortex, we have an amazing amount more of dopamine. So it looks like dopamine is what makes us, besides having a big frontal lobe, the fact that we have lots of dopamine there, and therefore excellent working memory capacities, that differentiates us from other primates. Now, long-term memories are formed by synaptic changes, so changes in the strength. You can see these neurons start off small and gradually grow. Okay, and for example, if they did experiments on rats and mice, and found if these rats were allowed to develop in a very rich environment with lots of toys to play with and mazes to run in, they would develop larger and thicker cortices. So these synapses would be much stronger depending on the the type of development that occurred. And in the case of reflexive or procedural memory, they occur slowly through repeated activity to a stimulus. And we saw how these memories get formed. It's due to this synchronous activity. So these two neurons are firing at the same time. These guys are firing at different times. And the fact that they fire at the same time causes these synapses to become small, and at the same time, these synapses to shrink in size. And this type of plasticity is how you learn everything. So this is a picture of my oldest granddaughter, Riley, and she agreed to be a subject for this experiment, and this experiment in learning these procedural memories. So we'll start off with a subject that's naive, and she would not like to be known as a naive subject. She's quite far from being naive. And we'll look at classic conditioning. So she is naive in that she doesn't respond to either sound or light stimulus. There's no blink here. We're going to try to get her to blink to one or the other. So what we'll do is we use a stimulus which is blowing on her eye, a little puff on the eye, and she blinks. Okay? So this puff is a good teacher. You remember that we needed a teacher in the VOR. Well, in case of the blink, we need a puff of air. So now, how do we get her to blink? You'll notice all these puffs happen. What we want a teacher is to puff not to the puff itself. We want her to blink, not to the puff, but to the sound. Okay? So if we somehow I'm not doing it right. This program seems to have failed. I can't seem to. There we go. I can't. The timing has to be just right. You have to time the click, the sound of the click with the same time as the puff occurs. And when that does occur, then this senses increases this synapse. At the same time, this synapse is being decreased. So now, whenever the sound occurs, she blinks. Okay? But she doesn't blink to the production of light. So other stimulus that didn't occur at the same time as the puff don't get strengthened and don't produce this response. So this is the basis of all long-term memories, and trillions of such connections have occurred in your cortex, and those trillions of connections are unique to you. That's what makes you, you. Now this is procedural memory, and this type of procedural memory involves the cerebellum. It's like the VOR. And if you have a lesion of the cerebellum, then you'll eliminate this reflex response. And also, a lesion will cause all kinds of other impairment, besides losing this reflex. Your balance will affect it. All the skiing that you took lessons in will be disrupted. Okay, another experiment for you to try. Again, I'd like you to try this. Try This is your little finger, and this is the one nearest to your thumb. And put this on the table, and see if you can do this sequence of movements. Okay? Now do it faster. Okay, just repeat that again. And faster still. Okay? So you've learned that sequence and learned to do it fast. Now we're going to do next test. Try this other one. Okay? This is another reflex. Okay? Faster. And faster still. Okay, now try to do the first one again, as fast as you can. You may notice that it's harder to do that first one than when you first learned it. Okay? What happened was learning that second sequence interfered with your ability to learn, interfered with your memory of that first sequence. So the second sequence interfered with the first. So here we are learning the first sequence, faster and faster and faster. And then we learn the second sequence, faster and faster and faster. And then we tried the first one again, and we can't do it as fast or as accurately. That's because this new one disrupts this first one. This first one is still fragile. It's just something that you just learned. Now, if we try something different, we learn the first one. Now we wait a while and then practice the second one. And then we try the first one again. You find that it's not disrupted, because during this time, this one was able to consolidate and become resistant to the practice of the first one. Now, if we try something else, we learn the first one, then we learn test it, then we practice another one. Now it's just disrupted again. Why is it disrupted again? You know, we took between the first one and its re-practice, we took a long time, so we should have consolidated. Well, just practicing makes it more liable to disruption. Okay? So just because we practiced it, it now can be interfered with by a new one. Now, that seems odd, but there's a reason for that. Whenever you practice something, you want it still sort of changeable, because you want to usually you want to practice it again, get it better and better and better, and that's why these connections are still fragile every time you practice something new. So it has a beneficial, and similar things happen for somatic, episodic, declarative memories. And I should mention that it's why these episodic and declarative memories are liable, because they're so flexible still. When you remember them, they can be changed inadvertently. Okay, you can remember things that were false, and remember false memories. The other thing that is remarkable is that if you practice and then test how far class you can do after some time. And then you sleep. You test again after some time. Then you go to sleep. The next morning, you're better. And it looks like sleep improves the storage of these memories. We're still not sure exactly what's going on. Some people think it's REM sleep. REM sleep is called rapid eye movement sleep. It's sort of while you're asleep, but you see most awake. Whereas another type of sleep is a very slow wave sleep or a very deep sleep. And there's still controversy between whether this is important or this is important for this thing to happen, for the strengthening memories to occur. This also works for the declarative memories again, so it's important to get the good night's sleep with either plenty of REM or slow wave sleep in it. Now, where does these change in connections take place? Well, they take place if they're procedural things. They, for example, take place in the motor cortex. You saw here that initially you've got a small area, and after practice, that area becomes larger. Okay, so the connections for that particular pattern changes that area of motor cortex. If you're a violinist, okay, you usually use your left hand for the fingering, and that's a lot more complicated than the bowing. Okay, so your left hand is used more as a violinist, and so you can image a violinist in a magnet and look at the size of their cortex for the left hand and the right hand, and you find the representation of the left hand is much bigger than it is for the right hand because of all that practicing. And probably people measured your thumb area of those that you use texting, you'll find that your thumb representation is larger for both left and right thumbs, because often you use both for texting. Same thing happens in the auditory cortex. You can be trained to detect certain frequencies more than others. That's why, for example, the area that involves speech is bigger in your auditory cortex. That's a limited area of frequencies that involves the speech, but it takes up a larger space than it should. Your visual cortex also. You can see here, if you're lucky, this small little gap between these two lines. And you can learn with practice to detect this small little gap, and you make it smaller and smaller and smaller. And you'll learn to get this, with practice, very small gaps. But you'll find that detection for this gap will only occur for the orientation of lines with which you practiced. So if you had the same size gap with a line of another orientation, you would not be able to detect that gap as well. So somehow those simple cells being able to tune in is important. So procedural memories continue to be consolidated in the primary cortex, in the primary sensory and motor areas, even in adulthood. Okay, so not all plasticity is lost in like the critical period, as we saw in the visual system, for the development of these simple cells. And so there's hopes for us profs still. A very important study was done by Brendan Miller with a patient called HM, and this patient HM has become famous, at least for people studying memory. Now, HM, in his teens, had head trauma, and as a consequence of that trauma in his head, a concussion basically, he developed epilepsy. And that epilepsy got very severe so that it threatened his life. And as a consequence, to relieve this epilepsy, HM had this hippocampus and medial temporal lobe removed bilaterally. And that had an unexpected result on one type of memory. Okay, so he didn't lose all his memory, but just one type. So the hippocampus is located here on the underside of the brain. So there's the temporal lobe under here. You can see the gray matter, and the gray matter sort of ends here in the middle of the brain, so medial, and that's where the hippocampus lies. So they took out this part and this part in both sides of the cortex. Now, what did he lose? Well, his working memory was fine. He could still remember things with the same duration that you and I can. Okay. His procedural memories was okay as well. He could retain his old skills. He still retained his language skills. He could still learn new sports. But he had trouble with one form of declarative memory. He could still remember things that occurred in his past, things that occurred before the time of surgery. But he couldn't remember anything that happened after surgery. So he couldn't form long-term memories of anything that occurred after surgery. So a doctor would walk into his room, introduce himself, they have a good conversation. The doctor will walk out, stay away for a few minutes, walk back in, and HM acted as if he didn't see him. They would have long interviews testing him and everything like that. He was very conducive to these things because he didn't remember being tested previously. Okay? The previous test never occurred, so he never got bored of them. He used to write in diaries and then read them the following day and not remember anything of what he had written. Okay, so each day would be like awakening to something new. Now HM was relatively lucky in that he had a normal working memory, but there are some patients that get a much shorter working memory, and they would wake up and write down, I just woke up at 11 o'clock in the morning, and then they'd look at the page again and cross it out because it's now, 12 o'clock. They'd cross it out and I'd write the thing again. I just woke up at 12 o'clock. It's a strange world to live in. So this is called anterograde amnesia. So this is the time of the lesion. And anterograde things, he forgets new things. He cannot form new long-term memories. He can remember everything in his past. Those are retrograde amnesias. So he doesn't have that. That happens more in terms of senile professors. And when you get things like Alzheimer's. Now, this is a picture of HM, sort of when he was relatively young. He died in 2008, so almost a decade ago, and he was 82 at that time. And remarkably, he could recognize himself in the mirror in his old age because he remembered himself as a young man and couldn't remember this image of this person standing in front of him. And he, of course, didn't remember all the tests that were run on him and all he did for the history of how we use memories. So how does this all work? How do we encode declarative memories? So we perceive things, let's say visual things, and they go through the visual areas like fusiform face area, and then they enter your working memory, and they're converted to, like a face would be the picture of the face would form the object-centered reference frame, and that face would be stored temporarily here in your working memory in the frontal lobe. And then you would go from there to the hippocampus. Okay? And unlike procedural memories, the hippocampus is a very good teacher because you could learn that fact in one try. So you see a person, you can learn that face in one exposure. You hear a telephone number, if you're attentive, you can remember that telephone number in one exposure. Because the hippocampus is an excellent teacher. Now the hippocampus, as I said, is located here in the medial part of your temporal lobe. So you've got your gray matter going around, then up here, the last bit of your gray matter in the cortex is this part called hippocampus. Now this is a very unique part of the brain because it's where new neurons are born. Okay, and you get not many, but about 1,000 every day, and they migrate to various parts of the cortex. And this is similar to the olfactory bulb, which also produces new neurons. And it evolved from the olfactory bulb, and so retained much of its properties. Now, as I said, this hippocampus is a good teacher, and that's because the hippocampus is well connected. It gets information from all of your cortex, particularly all of your association areas. And you can see here that these three little dots enter the hippocampus and come out and reform connections. And a third dot is born, a new memory, new association occurs. And so the hippocampus when it sees a face, it remembers, causes the memory of that face, a permanent memory of that face, but at the same time associates it with, let's say, you heard a voice before, or that person speaking at the same time as you see the face. It forms this association between these two facts. And it's hundreds to thousands of these associations that form your memory of different objects, like your grandmother. Now, when you form these long-term memories, changes the structure of the synapse, and in turn doing so involves structural changes, which means that genes that are expressed and you synthesize proteins. Now, what HM teaches us is that your memories themselves are not stored in the hippocampus. They're stored elsewhere. So when you see a face that has been stored previously, you can recognize that face. If you hear a voice that has been stored previously, you can recognize that voice without the hippocampus. Okay, HM was able to still recognize his parents, assuming that their facial characteristics didn't change too much in aging. He could still remember. He used to was good at doing the lawn because he remembered where the lawnmower was and remembered how the path was through the yard. Okay. And he learned to play golf well. It was a good, so even after surgery, he learned to play golf. But if you asked him whether he played golf, he would say no, because he would never remember playing golf. Okay, I think we covered this. So, yeah, it's a famous author describes how when he ate a cookie dipped in tea, that produced a flood of memories, because he'd have the smell of the cookie and the taste of the cookie, and it would activate many things in his memories that associated with those things. And of course, a lesion in different parts would produce a loss of a particular aspect of that memory. So, for example, the color of the cookie could be lost by lesion in some part of the cortex. Now, the hippocampus creates all these associations, and it can also be used to help us navigate, form a map of the world around us and help us find our way home. Now, this has been studied extensively in rats and mice who also have hippocampus, and who in their hippocampus have cells that are called play cells. And these cells fire when the rat sees a particular location. And these locations are associated with certain visual landmarks, auditory aspects, somatic aspects, and olfactory cues. Now, these place cells have been studied extensively in the hippocampus, and what they use is something called the water maze. So you can imagine this is like a kid's swimming pool, and you fill this pool with something that's like milky water. Like you added milk to a lot of water, so to obstruct anything below the surface. And then you'd hide a little platform somewhere here, and you'd ask the rat or mouse to find it. So you put landmarks, visual landmarks around it, hide the platform, and then the rat place a rat into the maze. And rats don't like to be in water, but they swim well. And so they swim around and find the platform and then stay on the platform. But if they have a hippocampus, next time you put them on the platform, they'll head straight for it, based on the memory of these visual cues. So these place cells can see fire, helping the rat find this platform. So they store the location of this platform on the basis of the cues. So the key step is to, when the rat reaches that platform, to remember that this platform is in a certain relationship, association to this arrangement of the cues. Now, if you lesion the hippocampus, the rat might get to the platform, but he'll never remember the location of the platform. So you can place it day after day after day, and the rat will never remember its location. But if you teach the rat where the platform is and then do the lesion, the rat will remember its location. Okay, another aspect is how is working memory and your long-term memories help you make very critical decisions. This is the type of thing you do every day. For example, you're in your house and the telephone rings. You can tell from your visual cues that you're in your house. So your working memory says, okay, that's where I am. And you hear the sound of the telephone. And you pick it up, because that's the thing to do in your house. If, on the other hand, you hear the same sound, but your visual cues tell you you're in your friend's house, then you can make the decision not to pick the telephone up. So it's those decisions based on these long-term memories and your working memories is what allows you to choose between one and then the other. Now, a very important part of the cortex, tiny little part near the hippocampus, is called the amygdala. And it is where all your sort of emotional responses are stored. So it is whether you like something or dislike something. And you can associate sort of dislikes with autonomic responses to that dislike. So if it's a line that you see, well, you certainly start sweating. So this won't happen, but I'm going to try to train you to dislike blue. If this was a big horn, imagine in these tests, huge foghorn. So after a few practices, you have to turn up your speakers and get. So what happens here is that this horn is supposed to increase your connection to blue light. So you can see again every time the horn happens at the same time as the blue light, you get this. Now, if you're a normal person and you see this blue light, it will cause you to sweat, even though you no longer hear the horn, like the blink in my granddaughter's case. But if you've got a lesion of the amygdala, you won't be able to produce this association of fear with the sound. So a patient with a lesion of the hippocampus will not remember which color was associated with it, but he'll produce the sweating still. Now, so the amygdala is required to consolidate autonomic responses to a stimulus. It's also involved in all kinds of emotional tones. It gives you a sense of fear or pleasure, and in a moment we'll see it gives you a sense of familiarity. Your amygdala is also involved in causing the release of all kinds of hormones from the adrenal gland related to stress, like epinephrine. Now, we saw the fusiform phase area, and it comes through the ventral watt stream, and it what gives you the conscious identification of who that person is. But at the same time, a signal goes through the amygdala, which gives you an unconscious autonomic response, a sense of familiarity. And this pathway is a lot faster than this pathway. And so often the sense of familiarity precedes you recognizing who that person is. And of course, that recognition could produce different factors. You could have a fear response and change in your skin conductance due to sweating, and that's the basis of these lie detectors that are used to test potential criminals. So if you have a lesion in different parts of the circuit, first of all, if you have a lesion in the fusiform face area, okay, well, you'll get a sense of familiarity. You'll see faces, they'll seem familiar, but you won't be able to recognize who they are. Okay, so if you have your parents appear in front of you, they're familiar, but I don't know who they are. You can recognize, at least visually. But if you have now a lesion of the amygdala, you have the opposite effect. Okay, here you know who they are. They are my parents, but they don't seem familiar. So there's a case of a patient who did have that lesion, and he claimed his parents were taken over by aliens, so that they're not really who they look like. And so he lost all sense of familiarity, even of himself in a mirror. So he could see that's his face, but it didn't seem familiar to him. But of course, his parents were still familiar if they talked to him by telephone. Okay, let's see how fast you can recognize faces. Hit the table as fast as you can if one of these faces seems familiar. Good. It's amazing how quickly that response is. It takes you milliseconds to go through all your cortex, to recognize the face in your fusiform face area, and you see it in different parts of the retina, and it gets coded, and you produce a hand response. It's an amazing feat. And what's more amazing is that we really don't know how it happens. Okay, that's it. Thank you. Good luck on the exam. I think you should find it not quite as difficult as the midterm.